projects, and he's also a member of Machine Learning and Optimizing Group at IIIT Allahabad. So I would like to invite Professor Shekhar Verma sir for delivering his talk. So hello sir.
Thank you for the kind words. And I think the whole thing was an exaggeration, but don't take it at its face value. And the biodata is a little old as well, but then currently I work in machine learning most of the time and security. And without much ado, I'll be talking about deep learning for photonic structures. Basically, it will be deep learning for design of photonic structures. And I don't profess that I'll be talking about the design as such, but however, I'll try to show you that this is a very important area, becoming important by the day. And it is one of the techniques for designing photonic structures, apart from other very powerful available methods. And obviously, in future and near future, all the techniques are going to amalgamate. They are going to be hybrid techniques, which will be there for development of photonic structures. So let me share my slides and quickly start. And I believe so I'll just request Professor Krish Tiwari to tell me if the slides are available or not, or visible or not.
Yeah, it is visible, sir.
Okay, so let's have 1.5 hours of deep learning for photonic structures, and I'll try to break the whole lecture into 2 parts. Number 1, some general lecturing on the application of deep learning for photonic structures in general. What are the techniques which are available and what are the techniques which are being developed? Second, we'll take 1 or 2 case studies of what is happening recently in the application of deep learning techniques for photonic structures. And as I said, I'll not be talking about deep learning as such, because you already had a wonderful session with Dr. Satish Kumar Singh on 5th. And I believe you are quite comfortable with the idea of machine learning and deep learning, especially deep learning structures. So I'll be assuming that, but I'll just be assuming it. Though this lecture will be complete in itself, but if you see it together with the lecture of Dr. Satish Kumar Singh, probably it will be a more complete session for you. So I'm Professor Shekhar Verma, as already announced by people and by the organizers. I work in IIIT Allahabad, work in the area of machine learning, deep learning, and security. So let's see what is happening in photonic structures. Again, though people may have told you a lot about this, but let's understand. So we are talking of controlling light and interaction of light with matter. And we have photonic crystals, we have metamaterials, we have plasmonic nanostructures, which have unparalleled capabilities. And what are we doing all this for? And they are able to tailor or customize light matter interactions. And while they are doing it, they unlock new device concepts which were not there, probably not there in nature itself, though tomorrow we might find that most of the materials may exist in nature. We have just not been able to discover them. But as of now, we say that there are new device concepts, new devices, which may not be so visible to us in the nature. And while we are doing so, many of the fundamental laws have been revisited. They are not as what we were seeing it in our theory classes or in our mind. And they can be revisited or generalized. And as we do this, and we know all engineering, all medical is an application of physics. And as soon as we revisit or generalize the fundamental laws, obviously, they promise a wide range of very, very important applications, both unseen and seen applications. So let's see. For example, photonic crystals can realize complete photonic band gaps. And this says that light can transmit around a sharp bend surrounded by such crystals. So here is one ready-made application which is already there, which is optical transmission, which has a loss of micro bends, macro bends, and optical fibers. And we can have lossless transmissions along sharp bends inside the body, outside the body, long haul transmission, short distance transmission, all will benefit from this. And this can work with near perfect efficiency, which means there'll be no loss and we don't need amplifiers ultimately. What do metamaterials do? And you already had a session just now. They demonstrate exceptional properties through a structural design. And for example, the whole physics that conventional physics laws that we had on our head, it can, for example, enable light to be refracted in negative direction and have negative refractive indices, which is something which the normal materials do not exhibit and metamaterials exhibit. Again, for example, we have plasmonics, and by using metallic nanoparticles with different sizes, geometries, compositions, plasmonics can actually break the classical diffraction limit. And this says that we can control light emission at a single molecule level. And this becomes very, very exciting. But more importantly, when you look at it in a little more detail, look at the photonic crystals, look at metamaterials, look at plasmonics, what you find is that the chemical composition takes a backseat and the structural designs, they start playing a central role. That is, the geometry starts playing a central role in the design of metamaterials, in the design of plasmonics, in the design of photonic crystals. And the versatility of photonics can be attributed to strong relationship between device geometry and the corresponding optical response. And the device geometry controls or allows many optical properties and functions to be tailored. So if you can control the device geometry, you can tailor the response, optical response, and the functions. And obviously, given the material, you can use, for example, the structured dielectric and metallic crystals, and thereby, once you choose the crystals, the device geometry becomes very important for eliciting a particular type of optical response, which can be customized or tailored. So now, let's see what we really want to do. For example, let's take a photonic crystal. And for example, you have some periodic layers of refracting materials with different refractive indices. And we can control the light within that. And through this we can emulate, for example, a waveguide. We can emulate something like a semiconductor. So you can have a photonic semiconductor, for example. But then, using the optical laws, using these laws of physics does not help us. It gives only a framework. It gives a guided light. It will show some general characteristics, but you'll not be able to design something. So what should we do? So the second method that came into being was using electromagnetics or computational electromagnetics, in which we may use time difference. For example, you might use finite difference time domain techniques, in which the whole structure can be seen as a mesh. You do some computational electromagnetics, discretize the Maxwell equations, and find out the electromagnetic response corresponding to a particular structure. So this gives a second line of thought. We can have Maxwell's solvers using finite difference time domain or FTTD techniques, but they are highly computationally intensive. And what do they solve? They solve what is known as a forward problem, or this forward problem or the direct problem in which we say that given a structure, what will be the electromagnetic response? And the solvers that we have are able to solve this, and for a given structure, we are able to predict what will be the electromagnetic response. However, when you look at the whole design, I have a very complicated structure, a meta surface, for example. I solve it using some solver, which solves discrete Maxwell's equations using some initial and boundary conditions. I take some hours or days to solve it, and I get the electromagnetic response. But then if I don't have the desired optical response, electromagnetic response, I like to tweak the material. When I want to tweak the material, then I'm in a soup. Because I do not know how to tweak, what to change, what is the customization in the structure that needs to be done. And if I take random structures, then I'll spend so much amount of time, because the whole problem is so non-convex. So non-convex that solving each one of them and getting the required structure which will give me the desired optical response or electromagnetic response is almost impossible, because the relationship between the structure and the corresponding electromagnetic or optical response is highly nonlinear. So what happens is, this is what is the inverse problem. Given a desired electromagnetic response, how does one find a suitable photonic structure? And this problem is what, because multiple photonic structures can give the same electromagnetic response. That means the problem, if you look mathematically, has a lot of local minima, but finding out the global minimum is somewhat, you don't have in this highly non-convex structure, it will not be search space or design space, you will not be able to go to the global minimum. Or we do not have a method which will go about in a very, very systematic way to give us solve the inverse problem, which is, again, I repeat, given the electromagnetic response, how does one find the structure? From the structure to the response is fine. From the response to the structure, the inverse problem is very hard to solve because of its very nature. So let's look at the forward problem once again. Given a structure, what is the electromagnetic response? That's a forward problem. The problem is easy, or easier, I would say, and can be solved using the well-established numerical electromagnetic simulators, which can solve Maxwell equations by taking a fine mesh, doing some discretization in the spatial and temporal domain, use a huge computing resource that we have nowadays at our disposal, run the simulation, give you the electromagnetic response. But what about the inverse problem I have been talking about? This cannot be directly evaluated. And as I already told you, the solution space is highly non-convex. So you cannot have a systematic way, you cannot use some gradient descent or something of that sort to reach to the global minimum. At the most, you can go to a local optima, but that may not be the best solution that we want. And this problem, from the response to the best device, is still challenging. And this is where machine learning steps in. So where does machine learning step in? Machine learning steps in to solve not only the forward problem, but also help in solving the inverse problem. And before we go in for and see why machine learning or what is machine learning, very easy. Instead of using some rule-based techniques or some physics-based techniques, principles-based techniques, let's see, we are going to use a data-driven approach. So originally we started with some rule-based or some physics-based, and we found that they give only guidelines. If you have multiple layers of modulating structures, then we can control the light. That gives only guidance. The numerical solutions are good at solving the problem, though they require huge and humongous amount of computational and storage resources. And while they solve the forward problem, solving the inverse problem is difficult. From response to structure is a problem which lies unsolved. Though there are some attempts using some optimization like evolutionary techniques like genetic algorithms or PSOs or particle swarm optimization or cuckoo algorithm, but the problem is largely unsolved in a satisfactory manner. So what we say is machine learning can help us here. And what is machine learning? Machine learning is a data-driven approach. It does not bother about rules. It does not bother about the physics of it or the relations. It just learns from data. So if you see what is the objective of computational electromagnetics is to capture the non-linear relation in a high dimensional space. Let's see what is this in a minute. So non-linear relation means if you have a relation y is equal to fx, then number one, f is highly non-linear, exponential and whatnot. And high dimensional means the total number of independent variables might range to millions. In machine learning, for example, in deep learning, we may have total number of independent variables, which we call features, may range to millions. And their interplay, because, for example, y is equal to a0 plus a1x plus a2x squared plus a3 into x1, x2, x3 plus a4 into this. So these a1, a2, a3, a4 are the parameters that you need to learn. And these parameters may also go to millions. So you have millions of parameters and you have millions of features. And there's a complex relation. And since the relation is nonlinear and the total number of independent variables go to millions, so we are in a high dimensional space. And capturing this relation using physics laws is possible, but very, very tedious. But using data to find out the relationship, which is highly nonlinear relation in a large number of hyperparameters or parameters like y is equal to mx plus c, m and c are parameters, x is the variable, and this is happening in a hyperplane. For example, the x is a vector and not a scalar. Capturing this nonlinear relationship where we have millions of hyperparameters which are m, c, a0, a1, a2, and when there are millions of features or variables available, this is the core strength of deep learning techniques, or so as to say neural networks. And they, as I told you, they learn this relation from data and can mimic the nonlinear physics-based relations like photonic system geometries and their electromagnetic responses, the forward problem and the inverse problem. So, what is a deep neural network? It is, as you can see, you already had an idea from Professor Satish Singh's lecture, but let me show you some figure. What is happening? We have an input, which is the data of the photonic structure, for example, which may have physical attributes, the device image, the device graph. If it's a filter, then it'll have some time domain response. All these are inputs. They are just made to interact with each other. So, for example, the input is x1, x2, x3, x4, and x5. If you follow the mouse, then the input, the output of the first layer is a complex combination of w1x1 plus w2x3 plus w3x3 plus w4x4 plus w5x5, a linear relation, which is then passed through a non-linear, for example, a diode or a non-linear type of a structure. So there's a non-linear interaction. And these W's are what are learned from data. So in one word, we do not assume anything. We give an input. We know what is the output, the desired output, which is the spectral response or device geometry or device efficiency or field profile. And we have this particular network, which is nothing but a function which represents the relation, the highly non-linear relation between the input and output. And where do we get the parameters of this relation? By learning through data. How do we learn is not important, but learning, you can imagine that there is a learning process like simulated annealing or backpropagation or some technique through which we can learn. And we learn from data. The input are the photonic data structures. The output we already know from our solvers or from our practical data. We know the input-output relation. So you make this network learn, and it is able to learn highly non-trivial relations. As written, as you can see, highly non-trivial relations it can learn. And once it learns, once it converges, then given an unseen new data, it will tell you what is the response. Suppose the relation is this, the relation is a linear relation, very hypothetical. The relation is y is equal to mx plus c. Now you are given y, you are given x. Now if you have 2 or 3 points, then the network will be able to learn m and c, because you have just 2 parameters, the slope and the intercept in a straight line. And only 2 points can define the straight line. So if you have the straight line, then given any other point, it will tell you that this is x1, what will be the value of y1. If it's a highly non-linear relation you have been able to learn from data, then given an input, it has learned, then given a new x, it will tell you what is y. As simple as that. The only thing is this particular neural network can learn and is able to learn very highly non-linear relations involving millions of parameters and millions of features or independent variables. That is, it can learn a very complex non-linear relationship in a very high dimensional space. So if you are able to learn the relation, then what happens? There are 2 types of networks in machine learning or deep learning, which is a subset of machine learning. You can have discriminative networks, which can learn from training sets. What is a training set, my friends? Training set is a lot of data that you gather from either simulation or from practice, in which the input-output relation is known. So you have known input-output relations, which can, as I told you, can come from surrogate electromagnetic solvers or electromagnetic simulation data that you already have, or you have data from experiments, and this you can use for training a neural network. Train what? Train it to learn. And when I say what is learning, learning is learning the hyperparameters. For example, in a straight line, learning m and c in y is equal to mx plus c is what is learning. So you are able to learn the millions of hyperparameters like m and c. For example, if you learn a polynomial y is equal to a0 plus a1x plus a2x squared plus a3x cubed plus a11 x12, something of that sort. So you are able to learn these a's from the training set. And where do you get the training set from? From either experimental data or from simulators. This is the discriminative network. What does a generative network do? Now, this is interesting. The generative network is able to learn the probability distribution function or probability distribution of the geometric features. Now, for example, you have a metasurface and there are holes. So from hole vectors, you are in a position to learn what is this particular probability distribution of the structure will give this kind of response. So generative networks can learn the they can learn geometric features in device distribution. So you have a distribution of different structures, and the generative network can learn this geometric feature, find out what is the underlying distribution, and can create more structures which have the same distribution. For example, if the distribution is a normal distribution or a Gaussian distribution, it can learn it and generate more devices which will have structures which follow the same distribution, and hence can be used to generate data or can generate similar photonic structures. Similar in what sense? Similar in the statistical sense. So let's see the discriminative models. So in the discriminative models, it's a forward learning. That means it's able to infer knowledge from training data to perform classification and regression. What is classification and regression? It is learning the input and output. For example, in your college, you give the marks of students, and you say who good, very good, excellent students. So you give the marks, it will be able to classify the students into good, not very good, or not good, very good, and excellent. So once you have the training data, then given the marks of an unknown student, it will be able to classify the student as excellent, good, or very good. But this is a one-dimensional. If you have, say, marks in 50 subjects, marks in 20 subjects, his medical data, his height, his everything, and then I wish to classify the fitness, then given 100 independent measures of that particular person, then also it will be able to classify. And if the output is discrete, countable, then it is called classification. If the output is discrete, uncountable, then it's called regression. So very simple difference. So here let's see. So the input, for example, are physical variables, and the physical variables of a photonic structure can be the geometry in which it will have thickness, diameter, width of holes, etc. The incident light, the frequency, the polarization, the material type, which can be characterized by the permittivity and permeability. You give this as input. And we know from the electromagnetic simulator as to what is the relation already. So you are able to give input and output in a discrete manner, train the network. So initially all these lines which you see are connections have random weights, W1, W2, W3, W4, W1000, W million. These are random. So when you give the input, it will give you some random output. But do you know what is the desired output in the form of physical responses like transmission, electric field, band structure, radiation pattern? You find out the difference between what is being generated from the network and what is actual you want, the actual, and this is the desired one. And using some technique, you are able to minimize the gap between, change these W's in a systematic manner, which is called training, to make the actual response and the desired response come close. And this is what is training. So in the discriminative model, you are able to learn F from given X, which are the physical variables, and Y's, which are the physical responses. So same thing in a simple manner. So given the specific response of the devices, you have the device space, you have the device response. The neural network or this particular network is able to learn in a systematic manner. Example, in the right hand side, we just show that it is actually able to learn for different devices. It is able to emulate and learn what will be the response corresponding to the device space. Given a lot of training data, it is able to learn this. Now, given an unseen physical data, given an unseen physical variable from an unseen device, it will give you the correct physical output. In highly non-linear with large number of parameters, still here the output is very simple. It's in just 2 dimensions. So here it's learning is easy. So here, in fact, it's one response. So you have a non-linear relation between Y and X, but there is just one X and one Y. But if this becomes a vector in, say, 100 million dimensional space or a million dimensional space, and output is also a vector, then that will be difficult learning. So how do discriminative networks learn? They just try to minimize. So as I said, in the training data, initially all the weights or parameters are random. So you, for a given X cap n, that means it's a vector, you get some Y cap n. And then you have some desired output, which is Y superscript n in parenthesis. In a systematic way, you minimize this, what is called the loss function, which is just a quadratic loss function, difference between the desired and actual. The first one is yn is the desired, y cap of n is the actual, and you define the loss and you minimize the mean square error. How do we minimize the mean square error? Is through learning, which I think Dr. Satish may have told you. Otherwise, also, it's not really important for you at the present moment. Suffices to say that there is a systematic way of changing the weights so that y superscript n comes close and close to y cap superscript n in a very systematic manner. And this is saying that this means that the network is learning. That means we have weights which are able to learn the actual response between the input and output. The generative model, my friends, the generative models are able to learn the underlying statistical distribution. So we have the input, we give a noise type of thing, which is a Gaussian or a normal distribution. We somehow change the parameters of the Gaussian distribution to emulate any other distribution. So given the input parameters, we are able to tweak and change the random normal distribution, not random, or random noise or normal distribution to any complex distribution which is governing the inputs. That means in one line, easily what we can say is that what do generative models do? They are able to learn the underlying distribution. The probability distribution function, the PDF, is learned. And if you learn the PDF, you can then generate more samples or more data. Or if you are able to learn, for example, an image, then if I am able to learn the image of, say, a scenery, then I can generate more sceneries. If I am able to learn the distribution of Mona Lisa portrait, perhaps I'll be able to generate more Mona Lisa portraits. Number of Mona Lisa's portrait, each having the same underlying PDF or probability distribution function. So example, using a generative model, here is an image application in which the model has been able to learn the underlying distribution of this lady with golden hair here, and this lady with a different facial characteristics. It is able to learn and hence mix and match. So here, if you look at this on the right hand side, you are able, these two are on the left hand side, my friends. We have images or portraits which are belong to real people. We are able to use and learn the PDFs and mix and match them to generate fake images or synthetic images. So if you are able to learn the images, the underlying distribution, then you are able to generate data structures or portraits or images which mimic this data distribution. On the right hand side, if you look, this paper which was reported in OSA Advanced Photonics Congress in 2019. People could generate large number of highly efficient metasurfaces by learning the underlying distribution. Then this network is able to generate more metasurfaces which have the same distribution. So also all these are distributions, as if you follow my mouse, they are distributions which are generated by a network after learning the underlying distribution of given metasurfaces. And this allows you to solve the inverse problem. What are we able to do? Given a lot of portraits, we are able to generate synthetic images or portraits that have the same underlying distribution. This makes it highly suitable for my photonic structures where structural design is important for eliciting a particular type of optical response or electromagnetic response. So if I can generate geometric structures or physical structures which have the same underlying distribution, perhaps I'll be able to generate structures and solve the inverse problem. And let's see how we go about it. So how do we really do it? So we find out what is the distribution. Finding out the distribution is just making the histogram very easy. So we know that there are pixels from 0 to 255, and we are able to make the histogram of this. How many pixels have how many values? So generate a histogram. I learned the histogram. So I find learning requires learning the difference between distribution. So my friends, we have two types of inputs. One, I'll just show you. One is the image that you have, the histogram of the image. Second is the normal distribution or Gaussian distribution. You find out the difference between distributions. So the key to the whole thing is find out the loss function. What is the desired distribution? What is the given distribution? The given distribution is Gaussian. What is the desired distribution, which is given by the input portrait? Find out the difference between distributions. As you can see here, in the red, we are saying this is the distribution of the training data, which is the given images. This is the network distribution given to you as input. Then what we want? We want to find out the difference between the distributions so that we can minimize the difference between distributions. So for that, we define a loss function. As we have already seen that a loss function here, remember, was just the difference squared. Mean square error was the loss function. Here, the error of the loss function is actually the difference between, or the distance between two distributions, which is given by KL divergence, which gives the distance between distributions, or some cross entropy technique, which gives the difference between distributions. So we know the difference between distributions. We use the input images to somehow make the distribution, the random distribution P, come close to the desired distribution Q, which says that the network has now learned the latent distribution. So here is an example. And before we go to the example, here is what we are doing. We are trying to minimize the distance between distributions P and Q. And this is what is called learning the generative network. Before we dive deep into this, and let's look at some things. What can be the inputs? So let's go to the photonic world now. Let's leave the deep learning world and all these things. Let's go to the photonic world. And in the photonic world, let's look at this. What can be the inputs? In the photonic world, we can have discrete values as input. For example, the geometry can be an input to the network. What can be the input to the network? We can have the thickness, we can have the diameter, we can have the width of the holes, we can have the incident light, and the slide I've already shown you, can have material type, permittivity and permeability can be an input. What else can be an input? We can have images. We can just give images as inputs. For example, this is an image of a free-form photonic device, and since that cannot be described by a few discrete values, for example, an image can be described by a few discrete values, but a free-form device cannot be described by a few parameters. So you can give the image itself as an input. 1D vectors, 2D matrices, 3D tensors, or 4D tensors can be given as an input. Or what else can be given? Suppose you have a filter which has a time component. So we have in deep learning, we have techniques like recurrent neural networks or long short-term memory or temporal convolutional neural networks, which can take and which can capture the temporal or time sequences or time series also. So that can also be an input. So the input can be some discrete parameters, can be images, can be videos, can be any time sequence that you can have. And we have different kinds of deep learning techniques or deep learning structures or machine learning structures which can take in these types of input to learn. Remember, what you are learning is a non-linear relation in a very high dimensional space between input and output. And that is about all it machine learning does or deep learning does. Learn the input-output relation or learn the underlying distribution of the input. That is all we are able to do. And if we are able to do, we can learn when the input data is in image data. For example, the parameters are given. For example, we have meta-grading, in which we have inputs like the diffraction channels and the incident field. And this can be learned from a particular deep learning structure, which is called CNN. Suppose we have coupling involved. That means we have graph type of data. For example, if we have coupled resonators, then the geometry is important. The relation between the structure is also important. So we have structured like graph neural networks, which are able to take graph inputs and then learn the input-output relation or learn the underlying distribution or whatever. If you have time sequence data or time series data, for example, the wave filter, then we are structured like recurrent neural networks, or even we can have a mix and match of CNN and RNN, GCN and or GNN and RNN. So all these things are there. And to make the long story short, we want to learn, and I've been talking about learning. So in learning, we try to minimize a loss function, which can be mean square error or difference between distributions or cross entropy, or can be some other thing. So we can define a loss function, and then through learning, minimize the error between the training and the network response. How do we minimize the error? By changing the hyperparameters, which we are calling as W's. As you can see, the W's here, if you look at my mouse, the W in CNNs you can modify, or the neural networks, the weights you can know, or in this recurrent network also we can know what are the weights which will, or the parameters which will give the correct output. So let's recap quickly. So first, you must have a training set. Where do we get the training set, my friends? We get the training set from electromagnetic simulators that we have, or from actual experimental data. You make structures, measure, find out what is the response, and this is the training data. Or for different structures, you simulate, you find out what is the electromagnetic or optical response, that is the training data. From training data, you generate the training data. Forget about validation and test at the present moment. Initialize the neural network. The neural network can be anything. The CNN can be the neural network, this GNN can be a neural network, or this RNN can be a neural network, or there can be so many variations which are neural networks. You initialize this with random weights, which are the hyperparameters. Then perform the network training using this training data. You give input, get some output, and then in a systematic manner, change the W's so that you get the correct response. Once you are able to do this, then test it on unseen data. That means a test set that we have. And once you are able to do that, you know that your network has converged, your network has been able to learn the input-output relation. A very highly non-linear relation in a high dimensional space, it has been able to learn and converge. So let's see now. As I told you, discriminative networks which are able to learn the forward problem. And let's see. So number one, these surrogate EM solvers, once they are able to learn, once the training takes a lot of time, very highly resource intensive, but once it has learned, new device features go in and it will give you the optical response. So you don't need to solve a very, very complicated, time consuming EM solver. So you don't need to really do finite difference time domain, define a mesh, do finite difference analysis. No, that is not required. Once you are able to learn, then it can perform the inference. Given an input, you get the output very, very quickly. Let's see how quickly. So, for example, it might take some 23 hours on a Tesla Quadro GPU. It took 23 hours to learn and produce 815 million spectra. And once it learned, then it was faster by 8.2 into 10 to the power 5 times faster than the CST Microwave Studio. So, learning time may be done offline, but once it has learned, then it will give you the optical response of a particular structure very, very quickly. And what has already been done, my friends, in this, we have been able to, we means not me, we have been able to learn the optical response of photonic crystals, photonic crystal fibers, waveguide couplers, plasmonic waveguides. This we were able to do in 2012 to 16. Now we are able to do it for 2D grating coupler. And this, for example, has been reported just 1 year back. The photonic crystal cavity have already been modeled. Likewise, free space nanophotonic devices have also been done, right from nanoparticles, which were done in 2017, quite recent, to nowadays. We have metasurfaces being modeled, absorbers being getting modeled recently. And these are from recent papers of 2018, 19, and 21. Nanoparticle scatterers have also been modeled using different techniques. And for example, this is a fully connected neural network, has been able to learn this using 50,000 training points. What do you mean by 50,000 training points? That means we have been able to simulate or make 50,000 structures, find out its response, give it to this network, it learns. Now you give any new structure, it will tell you what will be the scattering spectra. And as you can see, the NN approximation, which is given in red, is very, very close to the actual response given by simulation. So the fact is that it's actually able to learn. Apart from this, a CNN or a convolutional neural network, which is a deep learning technique, can be trained to predict electric polarization. For example, here is a UNet, which is a type of a 3D CNN or a convolutional neural network, is able to take this input, a volume discretized input, to give you the electrical polarization of this nanostructure. Once it has been able to learn, then it can just predict. Given a new one, as you can see, it is able to predict. And it is able to predict, and it's close and sometimes outperforms the simulation. It's closer to reality, closer to the experimental results as compared to the simulation. Now, can we do inverse modeling? Can we, from the response, can we generate the structure? We find that discriminative models are not very, very good at generating the structure from the response. And this has not been very, very successful, though people have tried to use hybrid techniques and couple it with Newton's methods or other optimization techniques, GAs, evolutionary algorithms, PSOs, all evolutionary algorithm techniques, but not very successful. Why? Because we have one-to-many mapping, and one-to-many mapping is difficult to learn. And we find that the inverse design, we are not really able to learn, but though people have tried and were quite successful, but learning the one-to-many mapping, first what we do is we learn the discriminative model and then do the inverse model. Not very successful, but I would say that you try and see if you can really do it in your own labs using electromagnetic solvers and ready-made off-the-shelf neural networks available. Please try it. But here, what comes to us is what is the generative network. Remember what generative network could do? It could learn the underlying distribution. And when it could learn the underlying distribution, what it could do, it can generate more samples or more structures by looking at the underlying distribution. It has learned the underlying distribution. So here is a structure which has been able to learn the underlying distribution. and hence will be able to generate more and more structures which have the same underlying distribution. And two structures which are common are called variational autoencoders, which learn the underlying distribution in a latent space or a low dimensional space, and generative adversarial networks, which are called GANs, which have been very, very successful in generation of fake images, deep fakes, fake news. They are able to generate the fake images or synthetic images or synthetic structures which have the same underlying distribution. So the idea is very simple. We have a training data. Again, we are able to learn we are able to learn the underlying distribution, which is in the latent space. We say that underlying distribution is learned. What is the underlying distribution? The distribution which is underlies the data, which is training data. So, and then can be used to generate more samples. So what we can have is an unconditional network, and that means we have the data which has an unconditional distribution, or that means the marginal distribution P of X. Or we can have a conditional distribution which is Px given Y. That means given Y, what will be the distribution of P of X? So Px given Y. For example, say what is the age distribution of people who are highly successful? So you have a Y says successful people, X says age. So what is Px of Y in, for example, Prayagraj, Allahabad? What is the age distribution of professors, for example? Y is professors, X are the people residing in IIIT Allahabad. So what is Px given Y? What is the distribution of the faculty members given that they are professors? Or what is the distribution of people given that they are professors? P of X is what is the distribution of people, age distribution of people. Any person who lives in IIIT Allahabad or in this world. So we can have conditional distribution. You can learn a conditional distribution. You can learn the unconditional distribution from the training set. Or we can do some optimization as well in the latent space, which is the space in which we have learned the underlying distribution. For example, a GAN was used to generate the free-form photonic structures, and this was reported, as you can see, in Nano Letters in 2017. And the generative network could generate and could learn from complex devices and then generate new free-form images. One such structure is what is called a variational autoencoder. My friends, I'll not go into the deep down into the working of this variational autoencoder, but the idea is very simple. We have the training data only. For example, I ask you to enter from a door, go through a very small window. So you will squeeze yourself and go through a window. So I learned how you squeezed yourself. So that is the underlying latent space. So all people I invite through the door, ask them to squeeze through the window, go out. Then I'll know everybody is able to squeeze in a certain manner. So I'll know what is the squeezing technique, what is the underlying distribution. How do I look like when I'm compacted? So that's the latent space. So I'm able to learn the underlying distribution. That's the idea of learning when we use a variational autoencoder. I'm given some data. I pass it through a low dimensional space in which I learn the parameters of this particular distribution. And then I try to reconstruct the same image. I take the image, pass it through a very, very small window, which is the latent space, find out what is the parameters mu and sigma of the Gaussian distribution, and then try to reconstruct from the Gaussian distribution parameters, try to reconstruct the image. And through this I learn. This is what is variational autoencoder. And it learns by learning any arbitrary distribution from normal distribution by learning the parameters of that particular distribution. What are the parameters? For example, mu, mean, first moment, second moment, third moment, fourth moment. These are the parameters of the distribution that I learned. And for example, there was one paper reported in which a variational autoencoder would be conditioned to output free-form metasurface architecture structures as a function of desired spectral response. So the input is a spectral response. You are able to learn the underlying distribution of the structures which give rise to this particular spectral response. Again, what we do is we take a lot of H-shape, cross-shape, split ring shapes. From experiment, I know what is the response. Now I get a response and I know what is the structure, and I keep on learning. So what is learning? What the network is learning is the underlying distribution. What is the distribution? What is the statistical distribution of the structure which is given such response? So given the response, it is learning structures. Now I want a special type of response which I do not know what is the structure. When I give that particular thing, it will generate the structure. So it will be able to learn the free-form meta surface structures, and given a new spectral response of an unknown device which I have not seen, it will be able to generate a free-form metastructure or metasurface structure. That's the idea of learning the underlying distribution. Now here comes something which is the most interesting thing which is going on in the machine learning world, in the deep learning world, and also its applications everywhere. What it is known as is a very interesting idea. And a little bit of history. In 2016, this came from a PhD student known as Goodfellow. He was just sitting with his friends in a pub, in a bar, and people were saying that we are not able to generate samples from a distribution. That means if you are able to learn the underlying distribution, we are not able to get the samples because we are not able to get the samples. So he said, why generate samples from distributions? Why not just generate samples from similar samples? So the network says, okay, we will generate samples from samples which will have the same underlying distribution. So again, a slight difference. First, we were explicitly learning the underlying distribution in autoencoders. In variational autoencoders, we were explicitly learning the underlying distribution. He said, no, don't learn the underlying distribution explicitly. Just have a network which is able to generate samples which follow the input sample distribution without learning the underlying distribution. They are explicit learning. What he did was very interesting. It's something like this. And my friends, I want your attention here. Suppose there is an art forger. So we have an art forger and we have an expert. The art forger paints a Picasso, gives it to the expert. He says, no, this is not close to the real one. So the art forger knows what is to be changed. So he again changes the forged art and gives another forged Picasso to this particular person, expert. The expert says, okay, it is close, but still these problems exist. He again gives it to the art forger. The art forger again changes according to the recommendations of the expert and then again gives it back to the expert. And this goes on. So what goes on? The forger generates fake Picassos, gives it to the expert who finds out the lacuna. This goes back. And this goes on, back and forth till a point comes when the expert is not able to differentiate between the fake and the real. And this is where we say that the network has learned, the forger has been able to learn to create fakes or synthetic images which cannot be differentiated from the true images. Let's automate this, my friends. So we have a generator which is generating data. We have a discriminator which is trying to find out the difference between the actual and what it is given, the fake and the real. So first, the generator just gives some random data, some noise. It says, okay, it is far from actual. Change it in this manner. So you find out the difference between the two distributions, the distribution of the noise which was given and the actual art, actual image. So he again changes it. The generator generates new image, gives it. He says, okay, the difference is less now, but this is the difference. Depending on that, again it changes because it knows the difference and the direction in which it has to go. The generator, which is an automated network, keeps on giving new and new and new images. The discriminator, which has the training data, knows what is to be generated, finds out the difference between the two distributions. The distribution is actual and the distribution which is being thrown at it by the generator. And after some time, after 100, 200, 300, or millions of iterations if required, the generator will be able to generate new data similar to the expected data. That means we are able to generate fake samples which are as good as real. What you mean by as good as real? That means an expert will not be able to differentiate between the Picasso, which is generated by the network, by the art forger, somebody who's doing forgery, with the real Picasso, or between the Mona Lisa, actual Mona Lisa painted by Leonardo da Vinci, and the fake Mona Lisa which has been generated by the network. So my friends, from the point of view of the expert, the idea is that we are not explicitly learning the underlying distribution, which we are doing in variational autoencoders. We are implicitly learning the underlying distribution. So here it is. The generator is an artist which just throws the noise initially. The discriminator is the art critic with a neural network which says whether the image is real or fake. By a systematic way, the noise is changed into meaningful images depending on the response given by the discriminator, that this is the change required, and you are able to generate images which are close in distribution to the actual underlying image. So that means you are able to generate multiple metastructures or photonic crystal structures or plasmonic structures which are similar to the actual structures. So now, as you can see, a conditional GAN can solve this inverse problem. It is able to learn the basic types, as you can see, and the generator is conditioned on the spectral response. So we given a response, it will generate some fake, some noisy, some arbitrary shapes. The discriminator will say, or the critic will say, no, this is not good. You change it. So it will change it. And from the noise, it will be able to learn the underlying distribution by generating these structures which will give you the proper spectral response. That means the GAN is able to generate new structures not seen till date, which have when you unmute your microphones, please, which are able to generate the spectral response which is required. So what we are able to do, my friends, we are able to generate structures which have spectral response which is close to the response or similar to the response of the structure. So you are able to generate structures from responses. Now I give a response which is I want, and the network or the GAN will be able to generate a new structure which will actually be giving that response. So here it is. First, you have a lot of meta surfaces or meta grating, which are actually giving some response. Now, from the response, you learn these structures using a discriminative generative GAN. Now, given a new response, the learned network will be able to generate a new structure which will give you the desired response. So I'm able to solve a very, very important problem. You want this type of optical response, or this type of electromagnetic response, or this type of extraordinary response you want. The GAN, after learning, will be able to give you a metastructure or photonic structure which will be able to generate that kind of electromagnetic or optical response. And this is what is mimicking real devices. So we find that the GAN generated images, for example, these GAN generated images or patterns are able to give you the response and give you very, very high efficiency. And the benchmarking efficiencies, we find that the GAN devices are able to generate topology optimized devices which are robust, which have a very, very high efficiency, and which actually outperform all the other existing techniques as of date. See, the techniques, number one, electromagnetic solvers and others do not exist. From response to meta structures is a very, very complicated process. You'll have to find out the response of a current device. It is less than an expert will tell you what changes has to be made. You make it once again test it. So if in 10 days you're able to make one device and test it, here you can test new devices in seconds. In a fraction of seconds, you can generate thousands of devices and check it, tune it to get the correct answer. So we have time for studying one or two structures. So let's take a case study in which people have used deep learning techniques for design of nanophotonic structures. And this is due to a paper which was reported in IEEE International Conference on Computational Photography in 2018, a high impact conference. So what they did was, let's see, that sub-wavelength nanostructured materials can be used to control incident electromagnetic fields, that we already know, into specific transmitted and reflected waveforms. So we can have nanostructured materials which can control the incident electromagnetic fields, what is reflected back, what is transmitted further. And this can be used as a building block to actually make more complex structures for novel applications. So as you can see, if you look at the whole thing, this is a huge problem, because you'll have an iterative process. You'll have to do modeling. You can do model, find out what is the response, do nano fabrication, nano characterization, and then go back, take an expert. Or you can have finite difference time domain methods. You can have a fine mesh in which you can take long simulation hours for the forward response. Then again make the whole thing go back to the, and you do not know if your device that you have fabricated or simulated does not give you the desired response, then you do not know in what way you need to tweak. See, the whole idea is that since the search space is highly non-convex and a very, very high dimension, given a particular structure, you do not know what modifications is to be made so that your response goes closer to the desired response. So what we can, as I told you, the problem is from the device. If you have an optical response, number one, prediction of the optical response is very time consuming. and requires solving the discretized Maxwell equations using some FDTD packages. Moreover, since the relationship between the device and the response is highly non-linear in a very high dimensional space, finding out solving the inverse problem is not possible today. Obviously, tomorrow we may have techniques which might do it quickly, but today we do not have. So, as I told you, we resorted to what is known as the data-driven techniques, which are the CNN techniques. So, let's see what was the problem people started solving in this particular one case study that we have taken. So, what they said was that we have a man-made subwavelength structure, and the incident electromagnetic radiation interacts with the subwavelength structure in a resonant manner, gives to you an effective optical response, and the optical properties involve both polarization of the desired metamaterial, which is the polarization of the desired metamaterial is dictated by what? Is dictated by the geometry which we wanted and we're saying, rather than the chemical composition. So the interaction of the white light with the array of metallic subwavelength structures, which is there fabricated on a glass substrate, causes partial color transmission, which can be different for each polarization. So it's a polarization specific transmission, and it cannot be observed through a conventional microscope because we have gone over the diffraction limit. So the forward problem is predicting the optical response in both polarization of a nanostructure based on its geometry constituent. And what is the inverse problem? Given this far field spectral or optical response, if you can look at my mouse, finding out what will be the structure which will give this response. That is the inverse problem we want to solve. So we want to solve what is the forward problem? What is the far field optical response for a well-defined nanostructure? For example, this is the nanostructure. If you look at this table type of a thing, this is the nanostructure. What is the forward response? What is the optical response? And given a response, given a new response, what will be the structure is what we want, is the inverse problem. And solving the inverse problem, people started using deep learning techniques. So what this people did was they used a geometric predicting network to predict the geometry using the spectra, and a spectrum predicting network, SPN, for finding out the forward problem. So let's look at the geometry here. So this was the inverse. First, what they did was input the spectra and materials. That means this is the optical response and the material they are put into this. And the network, as you can see, is a neural network. It predicted the structure. So what was input? We had some vector of 43 samples and the range of 600 nanometers and 650 nanometers, with spaces of 25 nanometers. And there are 25 parameters which were input. What is the output that we got was, now there was some output which was the material structures. Now this structure which was made and that was input into another network which gave the spectrum. Now obviously the spectrum will not be the desired spectrum. So what we are now going to do, we are going to join these two into a network. We give the input, which was actually the output, optical response, but material, etc., which generated a particular structure. The nanogeometrical structure was fed into a sister network, which generated the response. Now, this response was the desired response. This predicted spectrum is what we are actually getting it. Use some training of this neural network to find out the nanogeometry structures so that the input spectrum and the predicted spectrum they become the same. So the structure predicted network and the geometric predicting network, they were trained in tandem, they were trained together so that both of them become together, and then the nanostructure geometry was predicted and people used it. So I'll just show you. So the whole thing was done using COMSOL also, which is a package. So people also used a COMSOL simulation, and this is the result that they got. The red one is the COMSOL prediction. The black one is what is the predicted. And as you can see, the deep learning technique gave you a response after learning. It could generate the different structures, which was very close, and were able to actually outperform the COMSOL technique. And not only that, COMSOL only solved the forward response. It predicted a structure. The DL architecture showed a capability for predicting the geometry. It could predict the geometry of the nanostructures based solely on the far field response of the nanostructure. So what it was able to do, my friends, it was able to predict the geometry purely from the far field response. And we could solve the inverse problem, that is predict the geometry in a very accurate manner from the responses. So this scheme allows a very accurate prediction of the geometry of a complex nanostructure and can be extended in an industrial setting for other physical and optical parameters. Let's take another case study, which is a more recent and very interesting case study of a nanophotonic power splitter. This is reported in Journal of Lightwave Technology in 2021, number 4. Recently in July it came, or April it came, I remember. So this paper, in which they designed and solved the inverse problem of finding out the structure of a nanophotonic power splitter from the response that we want. And why nanophotonic power splitter? Because it's a building block. If you are able to find out the geometry of a single nanophotonic power splitter, perhaps you can use it for designing photonic integrated circuit, because ultimately you will have, it's a signal passing in which you split signals and join signals. So the device goal that they took was split the input power at fixed splitting ratio between two output ports. So there is one input port and there are two output ports in which I want the input power to be split in any ratio that I want. The aim is that the wavelength response with insertion loss, the wavelength response should be flat. The insertion loss should be as low as possible. It should have very high efficiency, no loss. So what people did was they chose a very simple 3-port structure on a standard fully edged SOI platform. The input and the output ports were having 0.5 micrometer waveguides as connected using an adiabatic taper to 2.25 micrometer wide square power splitter. And the connection width is 1.125 micrometer. And I'll show you this. So this is the structure, both the top view and the side view of the cross section. The size was of the square region of the power splitter is 2.25 into 2.25 micrometer square. It's not 2 square. T1 and T2 are the output ports. R is the reflection. And this is the cross-sectional view in which we have SiO2, and then it's obviously 500 nanometers by 220 nanometers, the cross-sectional view. And we have holes, as you can see. So what they did was, in the paper, what they have done is they generated labeled data, because any data learning, database learning, or data-driven learning like neural networks or GAN, they all require training data. So what they did was they generated data using simulation. And the data had several whole vectors of size 20 cross 20 and a spectral response at the output and the reflection at the input. So this is the data that we have. The data has the whole vectors as the input and the spectrum at the output ports and the reflections. That's the output. And the whole is important because it's the geometric structure. The whole structure is important. Each hole has a maximum diameter of 72 nanometers, which could be fabricated on an established lithographic method. So what is the aim? The aim is that we want to learn the relation between hole vectors, HV, and the spectral response at the 3 ports, 2 output ports and the reflection at the input port. That is all. Very simple problem, but the scale, as you can see, is at the nanometer and the micrometer scale. So this is the etched, these are the holes, these are non-etched part of the topology. It was given to a neural network. We know the response from the simulation. So this particular thing, the forward design, was learned by the network using some technique, some learning technique like back propagation, simulated annealing, or some way of which we learn. Once you're able to learn, then given the wavelength, given the response, you want to predict what will be the structure or what will be the topology. So a deep neural network was used for forward and inverse modeling of the nanophotonic devices. The deep neural network took the device topology as input and the spectral response of the 3 ports as the output. And it could predict the transmission and the reflection spectra, that means forward learning. Once learned, it could predict, given an input, given the whole vector positions, it could predict the response. This was the forward. So this is the forward. Given any new topology, it could predict the response. What will be the reflection? What will be the output at the 2 ports? This CNN could do. So the splitter, 1:3 power splitter, gave a very, very good response, flat response. But if it does not give you, as you can see, the forward modeling is effective to accelerate the optimization process. It will tell you if this is the input, what is the output. But the forward network will not be able to give you what should be the structure which will give you the best response. And this, my friends, we wanted could be got from the inverse modeling. So here, what is the inverse modeling? We wanted to construct the device topology. Take the response, take the spectral output at the input, at the output, 2 ports, input port reflection, and output ports, the spectrum. And I want to generate the device topology, my friends. So this is the work of inverse modeling, in which we generate the unseen results out of the training data. And the training data took time in hours, as reported in the paper, and the inverse design could generate 40 devices in less than 1 second. The inverse. So once it learned, people gave it the response and said, what should be the whole vector underlying distribution? How should the whole vector look like? So it generated, using the network, it generated multiple samples. And as you can see, the sky blue or light blue are the stars. They are all points. They are all, the stars are all the training data. The red circles, dark blue circles, and green squares are the first round, second round, and the third round. These red ones, this red line is actually the desired one we want. And as you can see, after round 3 itself, the results started coming close. We found what is the splitting ratio. And what it did was, we used the inverse modeling to generate unseen devices for a target spectral response. And what we started doing, we found that If you use CNN, it does not do anything. What we want is a network which generates samples. Remember, if I say GAN, what it did, it generated samples which are similar to the distribution to the input sample. What does conditional variational encoder does? It explicitly learnt the distribution and then generated the samples. And let's show you the result. So this was the network that was used. So as you can see, we learn the forward response and then we learn the underlying distribution. This is conditional variational autoencoder, and then it generated the output. And this particular thing was able to learn, and this was a conditional variational autoencoder. As you can see, it is learning the distribution here. The latent variables in mu and the z. That means the latent distribution underlying PDF was learned. I'll not go into details, but the input was 20 matrices. The first channel is the whole vector of the devices. Second channel is the decoded spectral data, as you can see, 2 channels. Then we have different convolutional layers. Where did we get this? The forward response was learned from using the electromagnetic solver, which was FTTD simulation. And then the conditional variational autoencoder could learn and then predict and generate patterns. And we could, if you see it, the output which was generated, what we did was it generated a lot of samples, and the CAVE, that means the conditional variational autoencoder, could generate the distribution and optical characterization. The figure of merit that we had was so high, and this is the scanning electron microscope image of the structure predicted by the conditional variational autoencoder. It was fabricated by the authors, and they found that it gave extraordinarily good response. You can see that solid lines show they measured by fabricating the device, they measured the transmittance. The dashed lines show the transmissions obtained from simulation, and the measured value agree well with the simulated value. And as you can see, both the simulated response as well as the actual experimental response was so good. There were some ripples, which is not clear at the moment in 2021 why ripples are there. So there is a lot of research still to be done. But what we are trying to say is that the GAN or the variational autoencoders and their variants are able to generate structures from responses which are giving very, very good results. And you can have optical design integration. The forward response from the structure to the response prediction is very, very good. From the response to the structure prediction is also coming of age, though a lot of work is still required. So the deep learning techniques, my friends, are able to have demonstrated their immense potential in prediction for photonic structure design, optimization of a structure, and for materials and the prediction of entire optical systems. So no prognosis, my friends, need to be made. I don't want to predict, but these networks can give us unparalleled speed up in responses, because once the forward response is learned, then it is able to act as a surrogate solver for Maxwell solvers very fast. Instead of solving each time, taking hours together, months together to solve a problem, we can get the forward response. We can do it very, very quickly. So they can allow us for large scale photonic designs, because it can give you solve the inverse problem from the optical response or electromagnetic response to the structure, and that can have multiple applications everywhere, from high speed super resolution, because if you are able to control the light matter interaction, your imagination is your limit. So you can have different types of applications, different applications, not in just classical domain, but also in quantum measurements, meteorology, energy conversion systems, real-time detection, manipulation, super resolution imaging, and whatnot. And obviously going to quantum computers and things like that. So thank you, friends. Thank you so much. I think it's about time, and it is 1:15. So I think I have kept my promise to sir.
Sir.
So I'm ready to take questions, sir. If there are any questions, I'll be happy to take them.
So,
hello.
You are mute. Professor Tiwari, you have muted yourself.
Yes, sir.
Hello.
Sir, thanks for a very nice, really nice talk and giving us a new insight towards the deep learning techniques. And till now, we have only information about our techniques of experimental and simulation. But now there is a new way to think, to find out some new properties with the help of the deep learning techniques. So I welcome the participants to have, if anyone have a question, please.
Questions are rare in such remote domains, but still, if you have a question, I'll be happy to answer.
Sir, so even though if anyone is interested to have a question even later on, you may write your question to the chat box, and we will just transfer the question later on to Professor Verma sir, and he will certainly answer, and we will communicate to you. So let's thank again sir for his nice talk, and I hope sometime in future we will have some physical kind of workshop, and in that we will have more rigorous discussions so that
and hands-on sessions also.
Sir, आप mute हैं क्या, Sekhar sir?
नहीं, I'm not mute. I'm not mute.
सही. No, sir. Actually, your voice is clear, sir.
Also.
Sir, there is one question from one of participants.
Yes, sir. Please.
Sir, you in chat box there already written. You were showing a graph of flat transmission. What is the advantage of it over light propagation?
Okay. No, it's not flat transmission. It's a flat response that we want. So whenever we want a response from any system, we don't want it to be specific. If you want it to be flat across a particular bandwidth, we don't want to be, suppose I want a response between, say, 1 and, in the optical domain, we want a flat response. It should not be specific to frequencies. So when I say flat response, if you put a white light, it should not have different amplitude for different frequencies. So that is a flat response of a filter, of a device that is not related to light propagation. Suppose I give a white light input, it should not be that different frequencies in the output, the optical content will have different amplifications. So that is the idea of having a flat response.
I think, Ankit, have you got your answer? Okay. So.
Yes.
Yeah. So, thank you, sir. Thank you again.
Thank you, sir. Thank you for the opportunity, and obviously we'll meet tomorrow, and then we'll discuss further.
Yes, sir.
Thank you, everybody. Have a nice day. Have a nice workshop, evening session, and thank you for listening to me. Thank you so much.
Thank you, sir.
Thank you, sir. Thank you, Dr. Pen. Thank you, Dr. Krish.
So, Dr. Pen, just our next session will start at 3 o'clock, is it?
Yes. So I request to participants, they can rejoin this meeting at 3 p.m. for our next talk.